so I'm Matthew Hague. This is joint work with Jonathan Cockens and Luke Ong. So I'm from Royal Holloway in London, and Jonathan and Luke are from Oxford. So the basic theorem of the talk is that the downward closures of language defined by higher order pushdown automata are computable. So if you understand that, then you're basically done. So for the rest of the talk, I'm going to just kind of go through this and explain the various parts and the motivation for studying this problem. So the first two questions I usually get asked are, what is a downward closure and why am I kind of interested? So that's what I'll start with. And I'll say a bit about higher order programs, higher order pushdown automata. And then I have some slides on the techniques that we need. So some of these techniques are kind of general, that might be of general interest, and some of them are more specific. And I'll see how many of those I get through. So I'll start with the downward closure side of things. So downward closure is like a language theoretic notion. So we like languages in computer science because we kind of think of languages as being, say, the set of traces of our program. So a language is a set of words, and if we have a program, then we look at the set of things that that program can do as being a set of traces. So all of the actions and things that it can do defines a language. So the downward closure, if we want to take a downward closure, what we do is we take a word, so take any trace of our program, and we just start deleting, and we need to think about what subwords of that are. And to do that, we start just randomly deleting characters from these traces. So here we have, I'll put it the right way around. We have a word, A with two B's. In order to get the downward closure, what we do is we pick some characters. To get a subword, we pick a character, say this B here, and we delete it from the word. So let's see if I get the right one here. So if we just delete that middle B, we get the word AB. So AB is a subword of the word AB, ABB. Similarly, we might choose these two characters at the end, the first A and the last B. And if we delete those, we get another word, which is the word B. So B is in our subword of ABC. And if we keep doing that, we get a whole set of different words derived from the original word that we chose. So the downward closure of a language is what we get just by taking subwords of the words that are already in our language. So in particular, we take any word W that's in our language, take a subword, and if we find a subword that's in our new language, our downward closure. So this is the basic definition of it, and the remarkable thing about downward closures is that it's always regular. It's been known for a while. So no matter how complicated, or whatever fancy machinery you use to define your language, the downward closure is always going to be regular. It's always going to be very well behaved, and you can pretty much do anything you'd like to do with it. So it's a very nice kind of notion in that respect. But there's kind of a price to pay for this, because obviously, if you have the downward closure, it can't always be computed. And you can see that because if your language was defined by a Turing machine, so we can take the language and use a Turing machine to define what the language is. If we could compute the downward closure all the time, we could then just take the downward closure of this language and ask if the character stop appears in that downward closure. And if stop appears, that means that there is some execution somewhere in our Turing machine that results in the Turing machine halting. So if we could always compute the downward closure, we could always solve the halting problem. So obviously, we can't always compute the downward closure. But it's known for a few cases, so finite automata, pushdown automata, and patient nets, that we can compute it. And I've put some ellipses here, which at first sight might give the impression that there are loads of these results. But in fact, most of the other results are just slight variations on these things, adding a few extensions here and there. So in reality, there aren't that many results in the area. And you might kind of realize this if you take your favorite automata model and try and think about how to compute the downward closure. You end up sort of taking, say, an infinite state space and trying to chop it up in some weird way to get a finite state automaton that satisfies this kind of property of the whole word. And it's not obvious how to do that. But fortunately for us, Georg Zetscher last year presented at ICAL a general approach for computing downward closures. And that's kind of the starting point of the solution of this work. So I'll give more details about that in the technical part of the talk. So to start off with, I just wanted to give some examples of why the downward closure can be of interest to people. And the reason I find it interesting is from the point of view of verifying concurrent systems. So I'll give a couple of examples. So the first one is not really an example, it's more of a schematic general idea of how you might use it in some protocol for some algorithm for analyzing a concurrent system. And the second example will be more concrete. So here we have two guys, and they're going to decide, these are going to be two machines. So this might be one language, one machine, and this will be another language, another machine. And they're going to decide together whether they're going to go for lunch or not. So we might have a simple protocol that says, the first guy asks, should we go for food? Other guy suggests a sandwich, and they agree, so they go to lunch. So in general, you might have some kind of way of specifying what runs of your protocol lead to the two guys going to lunch. So you can assume that our protocol is simple enough to be specified by a regular automata. And these guys will go to lunch together if we can find some valid run in this protocol, so something that's a run of the protocol, such that the first guy can do it and agrees that this is a good execution, and the second guy can do it and agrees it's a good execution. So if we can find that, if we can find an execution that matches all of these three constraints, then these guys are going to go to lunch. So the problem is, can we find such an execution? So as I hinted at before, if these guys are actually implemented using Turing machines, the answer is no. We can't even decide if this guy will go to lunch on his own. So we're a bit stuck in that case. However, there are many machines where we can decide, whether they do something like simple reachability problem or something. So suppose that these guys were implemented by pushdown automata. So this guy's a pushdown automata, so is this one. Then we can decide whether this guy will go to lunch on his own. We can decide whether this guy will go to lunch on his own. But if we try to ask, is there some execution that both of them agree on, then we're in much harder water, because actually the intersection of these two is undecidable. So just because we can reason about this guy and this guy doesn't mean we can reason about both of them at the same time. However, if these guys are regular, we can do this. This is very easy. You just take the two guys, form the product automaton, or do the intersection of your regular expression or whatever, do it again with your specification, and you get your answer straight away. It's very easy to do. So if you remember, the downward closure, that's always regular. So if you have the downward closure of these two guys, we can use the downward closure instead, and then we can get an answer to the problem. This might not necessarily be a precise answer, because our downward closures can be somehow considered an approximation, because not everything in the downward closure is something that these guys would do. But if we're lucky, we might have some specification that's kind of sharp enough or smart enough to notice whether something has been deleted, that something's not quite right. So if we can eliminate all the kind of dodgy runs we introduced by taking the downward closure, we get a general algorithm for reasoning about the whole thing. So that's kind of a basic idea of how you might use the downward closure if you can compute it. A more concrete idea, so there's a result this is kind of a result that was in Conco last year. So it's about something called parameterized asynchronous shared memory systems. And this is a model where we have some kind of master process implemented in some way. We have an arbitrary number of slave processes. So all of these guys are identical. It's the same bit of code. And we don't know how many of them are going to be around. It could be an arbitrary number. We have some sort of global memory. And everybody can read and write to that memory. The kind of kicker is that they can't read and write at the same time. There's kind of a non-atomic kind of constraint. So this process can write something, and that'll be one step. In another step, he might be able to read something, but he can't read and write in the same step. So he might get interrupted, the contents might change between the read and write. So there's a bit of relaxation in that side of things. And Latore et al. Last year showed that reachability is decidable when these conditions are decidable. And in particular, the only sort of significant restriction that they consider to be significant is that the downward closure of our master process is computable. Otherwise, all we need to have is that we can synchronize with regular automata. This is a very standard thing. You can pretty much do it with any machine that you think of. We want reachability of the slave to be decidable, so these guys. So this is not much of a constraint, because we can't hope to reason about the whole thing if we can't reason about one of them. So we have to be able to do something. So the real one is, if we can compute the downward closure of this guy, then we get this whole kind of concurrent system. We can reason about that for free. So really, we just have to be able to do the downward closure. OK, so that's kind of my motivation for looking at the downward closure. I thought I'd say a bit about higher-order programs to start off with. So first of all, why are we interested in higher-order programs? So if you're someone like me, it's not even a question. You're like, of course they're interested. But if you're not like me, you might want a bit more convincing. So I started looking at the kind of recent trends in programming. So higher order features are kind of showing up more and more in programming practice. So if you look at things like C++, which are kind of your low-level thing that you wouldn't expect many functional programmers to be playing with, they actually added explicit lambda expressions in 2011. They started to see the need for higher order features. Languages like Python and Scala, they're very popular, and they are just higher order. Especially obvious with Scala. Even Java, the kind of stalwart of object-oriented programming, has started to include lambda expressions since last year. And then there's JavaScript, which, whatever you think about JavaScript, is a very popular, very fashionable language. And when you actually program in JavaScript, you're actually doing higher order stuff all the time. Either if you're just using callbacks, if you're using things like jQuery, then you end up using them all the time. And Node.js, also based on continuation passing and stuff like this, all kind of higher order features, and it's difficult to get away from it. So I had an example here of some jQuery that so jQuery is like the de facto library for programming on the web. And if you wanted to load some information from the server and put it in your web page, you'd have an AJAX call. The argument to this AJAX call is a function that says what to do with the data. Then if you wanted to take that data and put it in your tree, you'd use your each function in the jQuery, which is another function that takes as its argument another function. So it's really, if you're going to write anything in jQuery, you're going to be passing functions to functions all over the place. So it's just a higher order way of using it. So we want to be able to, in our analyses, it's probably a good idea to start to think about how to include higher order programs. Okay, so how do we do that? How can we start to think about higher order programs? So in the first order case, the simple procedural programs, we already have pushdown automata. And these are very well studied, and they correspond to just the procedure calls in a normal program. So here's a simple factorial recursive program. And then here is a pushdown system. So in a pushdown system, basically what happens is whenever we do a procedure call in our program, we push another element onto the stack. And whenever we return from a procedure, we'll pop an element from the stack. So procedure calls are pushes, and returning is popping. So there's a very good correspondence with first-order programs and pushdown automata. And happily, if we want to start thinking about higher-order programs, we can take pushdown automata and turn them into higher-order pushdown automata. So I'm not going to say a great deal about what they are. I'm just going to show you this. A higher-order pushdown automaton, instead of having just a stack, what you have is a stack of stacks. So just like a higher-order function takes a function as its argument, a higher-order stack is a stack that contains within it more stacks. So here we have an order 3 stack because we have one big stack, which contains 2 stacks inside it, and each of these stacks contains another stack. So we have a stack of stacks of stacks. This is an order 3 program. Order 2 would be stack of stacks, order 4, stack of stacks of stacks of stacks. So the more nesting you have, the higher order your program is. So these have been around for a long time. They were introduced in the 1970s by a guy called Maslow. And the nice thing about them is, even though the stacks kind of do look kind of scary, the model checking problems tend to remain decidable. So we can do MSO model checking, LTL model checking, CTL, reachability. So all kind of model checking problems are decidable for these things. And I also wanted to mention quickly that they're equivalent to safe higher-order recursion schemes. And by that, what I really want to emphasize is that there are more general models of higher-order programs that exist. So you need to take away from that stuff. So the result we have about these is that the downward closure for these higher-order pushdown automata are computable. And this I like, it's interesting as, I think, as foundational theory, because me and Jonathan first sort of stumbled across the problem a while ago when we were thinking about concurrent analysis for these things. And we got to a much simplified version of this problem, and we thought, surely they did that in the 70s, but they didn't. So I'm very happy to sort of start to contribute to plugging that gap. But it also provides a tool with which to actually tackle the analysis of concurrent versions of these things. So there's the parameterized asynchronous shared memory stuff that I presented a few slides earlier. But there are also other results. A couple by Fauziatic I mentioned here are context bounds per thread, or a cyclic network for pushdown automata. If you delve into the proofs that these kind of concurrent systems work for pushdown automata, you find that they're actually using the downward closure in there as a proof step. So now that we know that that works for higher order pushdown automata, we have a way of generalizing these results for higher order programs. Okay, so getting on to the techniques. So there are kind of 2 parts to the kind of technique slides. The first I'm going to present Zetscher's general technique, which I think is of interest to anybody who's thinking about computing downward closures. And then if I have time, I'll say a bit about how we do it for the pushdown system case. So this is Zech's result, or the variant of it that's useful for us. So what he does is he shows that the downward closure for any class of languages is computable if we're able to synchronize with regular languages. So as I mentioned before, this is a pretty standard operation. So you can do that with any machine that has control states. The kind of difficult bit is solving the diagonal problem. So if we can solve the diagonal problem, we can compute the downward closure. So what is the diagonal problem? So I have a formal definition here. On the next slide, I have an example to try and explain it a bit more precisely. But the idea is we take a language that's in the class we're interested in, and we take a set of characters, A1 to AN, and basically the question is, can we produce an unbounded number of those characters at the same time? So for example, what that really means is for all k, for any bound we think of, is it possible to find a single word in L that contains more than k A1s, more than k A2s, more than k A3s, and so on? So we want to produce an unbounded number of all of these characters in the same word. Just to briefly mention, an alternative formulation of this, which is Zech's third formulation, is using the simultaneous unboundedness problem, which is very similar in flavor, but a little bit different. But here's an example of the diagonal problem in action. So here we have a language where we have words of this form. So the words have a certain number of A's, a dollar in the middle, and then a certain number of B's. So if we have one A, then we have one B's, two A's, we have two B's, three A's, three B's. We always put a dollar in the middle. And we can ask, what about the diagonal problem with the input, one A of the set being an A and a B? So does this language satisfy the diagonal problem for A? And it does that if we can find a word which has an unbounded number of A's and B's. So for example, if we say K, we can satisfy this by saying, taking a word that has three A's, a dollar, and then three B's. In fact, no matter what K we come up with, we can take that many number of A's, followed by that many number of B's. So this is a yes instance for the diagonal problem. However, if our input to the diagonal problem was just the dollar character, then this is going to be a no instance. And it's going to be a no instance because every single word in this language only ever has $1 in it. So for k equals 1, we can find the word easily. But for k equals 2, we're stuck because we'll never have $2 appearing in any word in this language. So if we can decide whether it's yes or no for our language, then we can compute the downward closure. How much time do I have? Okay, so I have a bit of time to talk about the pushdown case. So to start off with, the diagonal problem is kind of quite easy to solve by now for order 1 pushdown automata, for your basic pushdown automata. And you can, that's because the theory is so well developed, you can probably think of various proofs just off the back of the envelope. I just wanted to mention Van Leeuwen, I think, was the first guy to show this for the downward closure for pushdown systems. That's 1978. And in fact, in Zech's paper last year, he showed that it's even decidable for order 2. But what about for general orders, for an order n pushdown system? So our general plan of attack will be to take an order n pushdown system and reduce the diagonal problem for that system to the same diagonal problem for an order n minus 1 pushdown system. And then once we do that, we can repeat the process, get an n minus 2, n minus 3, n minus 4, and eventually we're going to end up with an order 1 pushdown system for which we can answer the question. So if our order 1 pushdown system is a yes, then the whole thing is a yes. So we want to just reduce level by level until we get to the point. Okay, I have a minute. So the reduction idea, so this is mainly for people who like pushdown systems. But the reduction idea looks like this. If we take a run of our pushdown system, our higher order pushdown system, that looks like this. This has 4 A's in it. And I've drawn, you can just about see I've drawn these little arcs on it. What that does is it matches, each order n push has an order n pop. So we can match pushes to pops in a run of our pushdown system. And then there's a fairly standard way, once you've done that, of decomposing that run into a tree. So basically, every time you have a push, you have a branch in your tree, an extra branch. So this bit here corresponds to this bit corresponds to this bit, and the leaves roughly correspond to the end of the arcs. The nice thing about this is that every branch in that tree can be run by an order n minus 1 automaton. So by doing this tree decomposition, we can follow one branch with something that's one order below. So you might ask, is that enough, just following a single branch? And unfortunately, the answer is no. In the worst case, even though this tree has 4 A's in it, this branch only has one A in it. And in fact, we can come up with a word where every branch only has a single A in it. So that's not good. It doesn't preserve our diagonal property. So we have to use something called logical reflection. And what that does is it's kind of clever. What that says is we can actually do fancy things with these automata, and these automata can actually reason about themselves. So they can say, at my current state, can I do something? If so, I'll do this thing, otherwise I'll do that. So what we're actually able to do is every time we get to a branch point in our simulation, the automata can ask itself, if I took this branch, would I be able to output some A characters? And if the answer is yes, if by taking the other branch it could have output some A characters, it's going to output one just to make itself feel a bit better. Similarly, at this branch, even though we're going up, the automaton can ask itself, could I have output A's on this branch? In this case, we could have output 2, but we can only output a single character. And if we do this, if we use this logical reflection technique to be able to make these kind of decisions, we can prove that this branch will actually have enough A's on it. So in particular, if the whole tree has k A's in it, we can find a branch that has log of k A's. So that's nice because if k is unbounded, log of k is still unbounded. So we do maintain the unboundedness property. And then in the general case, it's a bit more complicated, but it is possible. Okay, so that's basically everything I was going to say. The downward closures defined by higher-order pushdown automata are computable. This is nice because we can do the concurrent model checking for these things. There are also some other results we get for free. So one is separability by piecewise testable languages. So somehow that means if you have two systems, you might want to say, is there some approximation to the first system that still keeps me separate from the second? And with the downward closures, we can actually do that, or the diagonal problem, we can actually do that. And there are some other simple ones, like finiteness of a language. And I mentioned at the end Hague image, and that's because if you look at concurrent systems, pushdown systems, you often find they use the Hague image. Now this is fairly hopeless for higher order stuff, but often just the downward closure of the Hague image is enough. So by using the downward closure, we can actually get some Hague image style reasoning as well. For future work, I mentioned briefly that there are more general models. So in particular, I meant collapsible pushdown automata. And we still haven't figured out how to do downward closures for these things. For people who know these things, they'll probably think, well, surely the same techniques work. But unfortunately, for bizarrely frustrating technical reasons that you find 5 pages into your proof, it never quite works properly. So we'd like to kind of get that to work at some point. Second is to start to exploit this result for verifying concurrent systems. And also, the algorithm we have in this paper, it's not really practical. It's every time you reduce from an n to n-1, you blow up your automaton by a tower of exponentials. So by the time you get down to an order 1 system, it's unimaginably large. So it's not going to be a good way of computing that. And even if you did manage to compute that, it's not clear that Zeccher's result would scale either, because he's just enumerating regular expressions in a certain form. So there's a lot to be done about whether you can actually do this in practice. We might also think about bounded resource usage, so work by Dazanshi et al. They look about programs and how many resources they use, do they need a bounded number of resources, and they have various logics and automata for reasoning about this. So this diagonal problem has that unboundedness thing that we might be able to use to make some inroads into higher order versions of these problems. Okay, so that's everything. So thank you very much.
Hi, Deepak Majumdar from Max Planck Institute. So I guess I have a quick observation and a question. The observation is that because the emptiness problem for higher order automata already has a tower of exponentials, you're unlikely to get much better, right, for the downward closure. Because if you could solve the downward closure, you could solve the emptiness quickly.
So the problem is not that the tower of exponentials in the reachability problem, it's that the reductions are tower of exponentials. So it builds up and it builds up. So it's not just that you have a tower of exponentials of height n, it's of n squared or something like this.
I see.
Or possibly even worse than that. So, yeah, so it's.
And do you hope that you can actually get a linear tower of exponentials, like to match the?
So I don't have any intuitions on that. I can't imagine, I don't know how I would even start to break up the stack. So yeah, I don't know at the moment.
And I guess the question is that, I also asked Luke this, you could also think of the downward closure of tree languages with respect to the Kruskal ordering.
Yeah.
And the downward closure of higher order tree languages Have you thought about that problem and whether it can be solved?
I haven't thought about it until Luke mentioned that to me today.
Okay.
It does sound like an interesting problem, but I don't know about anything about it. Yes, yeah, of course, yeah. Ah, so that's my next one. That's the obvious one to do. I'd like to do that. But yeah, so this tree language sounds interesting.
So like for Pushdown Case, like the diagonal problems you just solve by
Yes, yes.
according to your idea, do you also use some Python HTTP?
No, we don't do that because the Parric image doesn't really work for higher order. We can't. I think finding a representation of it's difficult to start with, and it's possible to show that whatever this representation is, in order to maintain decidability, there are some quite restrictive constraints it has to satisfy.